In this video, we're going to cover implicit differentiation. An equation written in the form y equals something or f of x equals something is an explicit equation because it's solved for y. And we have specific rules and techniques for finding derivatives. An equation that has not been solved for y is called an implicit equation. An example of this is the equation of a circle centered at the origin with a radius of 4. Would look something like this. X squared plus y squared equals r squared, and so in this case that would equal 16. It's possible to write the equation explicitly if we solve for y. I would subtract the x squared and take the square root. So y is equal to positive or negative square root of 16 minus x squared. Now we treat this as two separate functions, one positive and one negative. Let's take the derivative of each of those. Now I've written it with a rational exponent instead of the square root, and let's just employ the power rule and the chain rule. So y prime is equal to half times 16 minus x squared, the inside, and if I subtract 1 from the 1/2 or subtract 2 halves from 1/2, that gives me negative 1/2 times the chain, so that would give me negative 2x. Perfectly fine to leave it like this, but if you did want to clean it up a little bit, I would probably cancel the 2's and then move all of this stuff with the negative exponent to the denominator and have a positive exponent. So y prime is equal to, how about negative x over, and since that exponent is a half, I can go ahead and write it with the square root. So that would be the derivative of that top half of the circle. Now the derivative of the bottom half of the circle, y prime, very similar. Negative 1/2, 16 minus x squared to the negative half times the chain. And let's see, I would probably simplify it just the same. So in this case, the negatives would cancel because we have a double negative. The 2's would cancel. I'd be left with x in the numerator and the positive square root of 16 minus x squared in the denominator. Okay, so there is a problem with implicit equations is that most of them cannot be solved for y. And so we need another way to find the derivative, hence the method called implicit differentiation. It's really just making use of the chain rule to find the derivative of each term with respect to x. And then we need to solve for the derivative, dy dx. So as long as we take the derivative of every term on both sides of the equation, we're keeping the equation balanced. So let's revisit that circle equation, but this time let's use implicit differentiation. So let's take the derivative of each term with respect to x. So the derivative of x squared would be 2x dx dx, the derivative of the inside function. Okay, so the derivative of y squared would be 2y dy dx. And the derivative of a constant, we know, is 0. So what you'll often not see is this dx dx, because that just equals 1. And so really, you'll see 2x plus 2y dy dx. Now let's go ahead and isolate the dy dx. So let's subtract 2x from both sides and divide by 2y. So dy dx is equal to negative 2x over 2y. And then maybe we'll just cancel those 2's, so this is equal to negative x over y. That looks much different than separating it out into two equations and finding those derivatives separately. Okay, in this example, we're going to find the second derivative using implicit differentiation. And we've got a quotient, so we're going to need the quotient rule. So let's just remind ourselves the quotient rule. Bottom derivative of the top minus top derivative of the bottom over the bottom squared. Okay, and I might rewrite this guy with the negative going with the x and the y on the bottom. So if I want to find the second derivative given the first derivative, it's going to be bottom times derivative of the top, which would be negative dx dx minus the top times derivative of the bottom, dy dx, all divided by the bottom squared. Okay, let's clean this up. So the first thing is that the dx is really just 1, and so we'll have a negative 1 times y, which would be negative y. In the second term, I would distribute the negative, or just multiply that, and I'm going to have a positive x dy dx, all divided by y squared. Now, there's one other thing that we have to be cautious about. You cannot write a derivative in terms of another derivative. So we need to make a substitution for dy dx. Well, that's equal to negative x over y. So let's just plug that in there. So my last step would be negative y plus x times negative x over y squared, and perhaps we'll go ahead and multiply the x with the negative x in the numerator. So negative y minus x squared over y squared. And that one's done. Okay, so how about this one? What's the derivative of this equation? And then let's, what is the equation of the line tangent to the graph? Okay, so a lot going on here. We're going to use implicit differentiation, and then what we got here is a little bit of the product rule going on. So let's get started. So the derivative of the first term would be 2x dx, which is just 1. I like to write it out. You don't have to. You can just leave it off if you want. Okay, so minus, and now let's do the product rule. Product rule is first times derivative of the second plus the second times derivative of the first. Again, if you want to just leave it off, that's fine. I like to show it. Okay, and then the derivative of y squared would be 2y dy dx, and the derivative of 19 would be 0. Okay, so let's see what we've got here. This is just 1, so this is just going to be 2x. This is just 1, so I have a minus x dy dx minus y, if I distribute the negative to both of those terms, plus 2y dy dx. Okay, so I need to isolate the dy dx. It's in two different terms, so I'm going to keep those terms on the left, move everything else to the right, and then I'll factor it out. So let me show you. I've got the negative x dy dx plus 2y dy dx. Leave those guys on the left. On the right side, let's move the 2x and the negative y. So I have y minus 2x. Subtract the 2x, add the y, and so that's what we've got. Let's factor out the dy dx. And let's see, that would give you negative x plus 2y. And we're about to get it isolated because I can divide both sides by that factor. And we have y minus 2x over negative x plus 2y. That's the derivative. Okay, so now what is the derivative? What is the equation of the line tangent to the graph at 2? Well, in order to find that, we need to have a point. I have an x value. Let's find the y value. So let's substitute in 2 into our function. So I'm going to have 2 squared minus 2y plus y squared is equal to 19. That looks like a quadratic. Let's go ahead and write it with decreasing order of exponents. So I have y squared minus 2y, and if I move the 19 over to the left, if I subtract it, I've got 4 minus 19, which is negative 15. That's factorable. Two numbers that multiply to get negative 15 and add to get negative 2 would be y minus 5, y plus 3. If I were to solve both of those, I would have y equals 5 or negative 3. So really, I've got 2 points, 2, 5 and 2, negative 3. Now let's evaluate the derivative at each of those points. So my next step, dy dx evaluated at 2, 5 would equal, let's see, 5 minus 2 times 4. Just kidding. let's try that again. Y value minus 2 times the x value. The x value in this case is 2. All divided by, let's see, negative x, so negative 2 plus 2 times the y value. All right, so let's see if I can do this. 5 minus 4 is 1. Negative 2 plus 10 is 8. So the slope at that point, 2, 5, is 1/8. If I wanted to find an equation of a tangent line, y minus y1 is equal to mx minus x1. And that is done. That's one of the line's tangent. Now let's find the other one. All right, so let's find the derivative evaluated at 2, negative 3. This bar right here just means evaluated at. So the slope evaluated at the coordinate 2, negative 3 would equal, and I'm using this slope formula here, so the y value, let's see, how about negative 3 minus 2 times the x value divided by the negative x plus 2 times the y value. And let's see, negative 3 minus 4 is negative 7. Negative 2 minus 6 is negative 8. So how about 7/8? And my point is 2, negative 3. So y plus 3 is equal to the slope, x minus 2. There's my other tangent line. Pretty cool. Okay, so this equation is an ellipse. And as you can see, we've got two tangent lines at x values of 2. Here's the 2, 5. Here's the 2, negative 3. And Mr. Sassman has shown us his work on those. So if you'd rather copy his, that's fine with me. Okay, so how about this one? One last example. What is the derivative of the equation x cubed minus 2xy cubed equals 18y? So a lot going on here. Our y is not isolated, so we are going to have to do implicit differentiation. Let's just take the derivative of every term with respect to x. So the derivative of the first term, x cubed, would be 3x squared dx dx. All right, so minus, I'm going to go ahead and leave the minus 2 out front, just treat that as a coefficient. And so I've got what we have here, product rule. So the product rule is the first times derivative of the second. So that would be times 3y squared dy dx plus the second times derivative of the first, dx dx, and equals to the derivative of 18y, which would just be 18 dy dx. Okay, so my next step is I'm going to go ahead and get rid of all of my dx dx's. That's just one. It's not going to change the value of that first term. And I've got this guy also not going to affect us at all. Let's go ahead and clean this up just a little bit. 3x squared. And let's see. I'm going to go ahead and distribute this negative 2 to this guy and to this guy. I've got two terms in there. And so that first one is going to be negative 6xy squared dy dx. If I distribute negative 2 times 3xy squared, that's going to give me a negative 6xy squared dy dx. Now a negative 2 times this guy would give me negative 2y cubed and equals 18 dy dx. All right, so that's all I can clean up. Now let's isolate the dy dx. So let's move the dy dx. I'll go ahead and move this guy to the right to make him positive. So I will have on the left 3x squared minus 2y cubed is equal to 18 dy dx plus 6xy squared dy dx. Now on the right side, let's factor out the dy dx. And that's going to give me 18 plus 6xy squared is equal to 3x squared minus 2y cubed. And my last step, to isolate my dy dx, divide both sides by that 18 plus 6xy squared. And I have 3x squared minus 2y cubed over 18 plus 6xy squared. Crazy, but that's the derivative. That is the derivative of this equation.